As I just mentioned in the previous class, what I would like to emphasize is on the failure mechanisms of stone columns, and we need to avoid this formation of bulging, and of course, that is inevitable. We should understand that the bulging is likely. Then we should also avoid this type of failures. I mean, this can be considered, these are all some of the failure mechanisms we should be able to understand in a proper manner when you are trying to deal with stone columns. In fact, IS code also highlights that there is a possibility that if you have a soft soil and then you have a somewhat stiffer soil, the possibility is that the stone column may not be completely effective, and you may have just shear planes going like this, and if the shear resistance is not sufficient, then the bearing capacity is likely to occur. So, possibly we should just look at this point, like was it correct, maybe you should go for increased diameter here or something. It is very important to understand that this is some of the crucial issues. There could be another thing like this, where you have in an inhomogeneous clay the soft soil somewhere occurring and then the bulging is likely, and the other possibility is that you have some more thick, it is a thicker strata and the bulging is likely. So, this one can get a feel of it from the actual investigation. Say for example, if you do a complete soil investigation up to say for example 15-20 meters depth, it will clearly highlight to you that you have some soft soil here, you have a stiffer layer here, and it could be a weaker layer there and all that. So, these sort of if d is the diameter and the h is that the height of this thing, there are some possibilities like this which can occur. So, this is one h is this thickness of the clay layer. Say for example, h by t is less than or equal to 1, the bulging is here, then it could be little larger also, of course. So, one should look for proper soil investigation and take care in this particular points. That is what you see sometimes in some places with the SPT, CPT profiles. If you do, possibility is that in some places you have some weaker values obtained, which means that the confinement was not really good there. So, as I just mentioned, this is the type of loading one can have. Say for example, if you have a water tank or some sort of loading, the possibility is that this is one type of the formation of the bulb. Here just you can have a single load, and then you can even design just to see that the stone column will take care of that load. This is one way, and the best way to ensure that the load is satisfactory, like allowable pressure. Say for example, you must have designed for 100 kPa or 200 kPa of allowable pressure, say for example 300 kPa of allowable pressure. You must be able to properly do an ultimate load test and also the measure the settlements with reasonable accuracy. A good experience with foundations and similar structures and calculations on the basis of principles of soil mechanics is important. The minimum factor of safety should be about 2.5, and the installation of techniques, we have seen some construction procedures by Keller group. Of course, people have been using this construction techniques in particularly in small projects, maybe not be if the big contractors may not come. So, the possibility is that people try to do their own technique of forming a hole and then putting the sand material and then compacting it. In fact, this is people followed in India, which is called rammed earth technique in about in 80s and 90s, when people particularly in Mumbai region, there is lot of expansion of infrastructure, and then there are no good companies coming forward to do construction work in India. People have devised their own methods. In fact, there was one Dr. Daitye, he is actually a retired chief engineer from Maharashtra PWD, and he knew about soil problems. So, he devised his own method, put a casing, ramming earth. It is a very appealing simple technology, and it was very effective in many cases. And nowadays only we see that big companies have come forward, particularly from Keller and other groups are trying to do something in India. But apart from it, in the previous times in 80s and all that, we have a creation of a hole in the ground which is later filled with granular fill or stone sand mixture and compacted to required strength. say for example friction angle of the soil. That is what people are doing. They did not have sophisticated methods. Then you have to construct a granular blanket, as I just mentioned, as per the IS code. You need to have a granular blanket of medium to coarse grain, about 70 to 80% relative density is laid with minimum thickness of about 500 mm. This layer is exposed to periphery, is exposed at its periphery to the atmosphere for easy dissipation of pore pressure. So, because there could be pore pressure mobilization in the soil, clay soil always generates pore pressures, because you are trying to introduce sand material or stone material inside, and then there is lateral pressure that is exerted, because the soil between the two columns is somewhat stressed. So, the pore pressure dissipation is there, which it is a pore pressure mobilization is a distinct possibility, and you should give an opportunity for the pore pressures to dissipate. So, what we do is that we provide a drainage blanket, we call it a drainage blanket, and we see that the pore pressures are dissipated. This is one important thing. And how do you conduct the plate load test? So, for example, on a single column, and maybe the 900 is the diameter of the stone column, and 1.85 meters is the spacing between the stone columns, and this is a spacing 1 point. So, you have a 1.94 mild steel plate with stiffness or RCC pad, and then this area is load tested. Okay, that is what the code says, and you can get the load displacement curve. Once you get the load displacement curve, you can calculate the ultimate load. See, like you to have a plate load test, we know, right? You have a curve like this, then you join the tangents, or you have 25 mm allowable settlement and all that. That is one thing. So, this is another one where you have a group effects, as I just mentioned. There are a bigger plate you have, like 3.36 PCC, pre-stressed concrete footing, you put it and then do a load test. So, this is also another one that the IS code recommends. So, it is very important that people go by these methods and do some plate load tests and get their this thing. See, one important thing is plate load test is one good thing, like we have derived expressions for the load carrying capacity of the single column as well as group of columns, 3 columns or whatever, it's just we can do that. But then the important thing is that the plate load test, we know that its limitations, right? It does not, the pressure bulb does not, like if the depth of the stone column is 10 meters, our PCC is 3.36. Our plate load plate is about 3.36 meters. Here the possibility is that one should be careful. So, best is that apart from plate load tests, we should do cone penetration tests, because we are doing it in soils. So, cone penetration tests are easy, they give a continuous profile, you will get exactly what you want, and you will be able to give the confirmation for the persons that there is no bulging at the bottom, there is no problem. Say sometimes we do not know how the column has completely formed. So, you can get some information about the formation of the column by seeing it, the signature of the ground, improved ground from the CPT profile, that is very important. So, actually I would like to just describe one design method that is very popular, that is used by Keller and other companies. Actually this is very innovative method as well. In fact, there are many design methods, one using limit equilibrium method, one is elastic analysis approach, and so in the elastic in the limit equilibrium approach, what we did was that we just by use of the cavity expansion, we are putting a sort of a cavity inside, and we are allowing it to expand, and we assume that there is a resistance from the soil. So, we are trying to equate what is the passive pressure and what is actually load applied like this. So, we equate it and we get this parameters in terms of cohesion and friction angle and all that, and then equate, and you get an equilibrium equation which will give you the actually what should be the lateral pressure. That is what we did, lateral pressure or whatever. So, and then in terms of the friction angle of the stone column. So, something like that, that is called limit equilibrium method. But then we have what is called elastic method also, which is also very interesting, and the vibro this has been very well used for vibro replacement method using stone columns. And the thing is that very important thing that one should understand is that the extent to which the density is improved or the properties are improved depends on the parameters of the soil, and sometimes most of the soils are difficult to measure. In fact, under the they are somewhat complicated. So, still you need to come out with some sort of design method. Actually here in this particular Pripe's method, what we do is that load distribution is there and also lateral support from the stone column. So, that is how you have a stiffened ground, and it gives an improvement factor. Say for example, you have loads that are you have a actual clay soil and then you have some stone columns. Definitely you have improved the area in terms of the, one can say that the improvement factor in terms of the area replacement, area, how much of area is replaced in the original soil. That can be an improvement, that can give an idea of the improvement. So, this improvement factor sometimes can indicate the increase in compression modulus, like you can do that consolidation test where you get compression modulus and the extent to which the settlement is reduced by the column ground improvement. So, here in this design what we see is that what is the improving effect of the stone columns in a soil which is otherwise unaltered in comparison to the initial state, like how is that the initial state has changed to improved state is what we are seeing in these methods. And it is very interesting that there are some simple assumptions in this method. The column is based on a rigid layer, the column material is uncompressible, which is of course stone material, still it has some compression. Bulk density of the column and the soil is neglected. Actually it is a serious interesting assumption. We do not really take into assumption, actually we really in some other, like in limit equilibrium methods we want the bulk density of the soil gamma b, then in this case we do not use that. So, what we do is that we will see how, I mean it comes later in some form, but these are some of the assumptions. One, we make some assumptions and we propose a theory and we correct for all the small things which are which are supposed to be critical. So, the other thing that we have, since the bulk density of the column and the soil are neglected, the column cannot fail in end bearing, and any settlement of the load area results in bulging of the column which remains constant over its length. Actually what we assume is that bulging is something, there is a small bulging which is constant in the field. That is what we assume, but we know that in the field there is a bulging differences are there, it depends on the overburden of the soil. So, actually we develop a simple method, understand its limitations and make corrections for it. This is what in the Pripe's method there is a simple difference, that why the method is elastic method, because it only uses a deformation modulus, then it is of course it uses the strength of the column also, like you will see that it has a number of parameters which are grid area, foundation width, cohesion, improvement depth, then depth of the ground failure, constraint modulus, depth factor, coefficient of earth pressure, proportional load on the stone columns, like which we just discussed, improvement factors, settlements, all these factors are there. And actually basic, we call it one term called basic improvement factor, we call it N naught. In the first step the basic improvement factor is calculated by using the following equation: A is a unit cell area and AC is the area of the column. Like as I said, any stone column it has some area that it influences, so that surrounding area becomes stronger. So, that is called area ratio, or that we call it the either AC by A, okay. And then this is the friction angle of the stone column. Actually this bearing this basic improvement factor is given by some simple expression, and we assume that a Poisson's ratio of 1/3 like 0.33 is taken, and the expression for basic improvement factor is simple, like how much of area is being replaced and how much of lateral pressure is developed because of the stone column placement. This is what it gives, and then if you just do a parametric, you can simply get some from Excel sheet what is the improvement factor and what is the area ratio one can have, and you can see that if the area ratio is very 1, which is close to, like you are trying to replace the whole material with stones, definitely the improvement factor is going to be very high, which is infinite, which is not possible, and because of the various assumptions that we have. Okay. So, like of course, in the this all for different friction angles one can calculate like this, and since it is not possible to have that particular thing, and then there is always a compressibility of the stone, there is a minor correction for it in terms of the these factors, and there is a additional correction to area ratio is given, and that is in terms of modulus of the column and the modulus of the soil. Whatever is the soil, there is a simple ratio that they have, and they use this correction factor for the improvement. This is one thing. What I would like to, I will just highlight some concepts in this, then there is a, I mean people can develop their own Excel program, or even there is a software available online or somewhere. One can use a software to calculate all the parameters, like using the stone column. So, as I just said, the neglect of see in the design method, it has some assumptions, and then it also gives you how to correct it for those mistakes, so that you have a good design method. That is a very nice approach, like you have idealized way of doing things, but you know that that idealizations are not possible. So, make corrections and give a final answer. That is a very good approach. Consideration of the overburden, the neglect of the bulk density of the columns and soil means that initial pressure difference between the columns and the soil which creates bulging depends solely on the distribution of the foundation load P on the columns and the soil, and that it is constant all over the column length. We assume bulging there is there, like all it's in bulging is everywhere, but we know that because of the consideration of loads and other which will be somewhat different, like bulging could be different in different places. So, there is another simple correction that they have suggested, which is in fact as a function of the overburden, and this is also again because of the overburden the improvement increases, the depth factor increases, like improvement factor, because as the depth actually bulging will be less at the bottom. Now, bulging will only occur at the top because of the overburden is less, right. Overburden is less and overburden is more at the bottom. So, when overburden is less, there is a possibility of bulging, because directly it is under the load and there is a possibility of bulging. So, for that there is some correction factor again, and then they have some correction factors, and for like this is that expressions for that, and actually this is an for the same mu s. And what are the shear strength properties of the improved ground also one can calculate, and there are some expressions here that are given. They are all what is the improved value of friction angle, what is the improved value of cohesion, and all that is given, and what is the proportional load that the soil can take is also as a function of the area ratio, like how much of soil total load is transferred to the stone column, again which is a function of phi of the soil, area ratio. These are all some understandable ideas, and then he also has some sort of expressions for settlement calculations, and then there is a simple example that we worked out, and again there is another factor that comes into picture here, and settlement ratio. In terms of the settlement ratio, again a number depending on the number of stone columns one can get this on a single footing. This is a simple expression. We will see that some of them in the actually it is a very useful contribution, because this is widely used in by Keller's group. Actually, in many others, many people are also must be using, but it is important that we have these some of these concepts well illustrated. So, this again for bearing capacity of the improved ground one can have some expressions, and like similar to our bearing capacity equation, and the factor of safety of bearing capacity you can get, and there is a design example that I try to work out. Where is the width of the top width of the embankment with the 1:1 slope, actually it is resting. Surcharge on the embankment is about 20 kPa, unit weight of the embankment fill is about 20 kN per meter cube, and the depth of the stone column is 6 meters. All that cohesion is known, friction angle of the clay, it is just a clay, is 0 degrees. All these column diameter I have assumed. So, some calculations are made here, and like basic improvement factor is about 2.3, then you try to get N1, then N1 if you just substitute, there is a marginal reduction in N1. Why? Because it reduces, as I just said, because of the dc by ds factor. This we have taken like assuming that these factors A, delta A by AC, these are all some assumptions we made, and one can get this. So, once even depth factor also one can make, and the final N2 one can correct, which means that there is a good improvement in depth, bearing capacity, and one can also calculate shear strength and all the other properties, and even one can calculate the factor of safety against bearing pressure. So, this actually are easily done by a simple software which can be is called StoneC. It supports the rectangular and triangular stone columns, and one should buy this. That is one important thing. It is available, and because particularly when you are in stone columns calculations and all, it needs lot of other you are going back and forth. It is always nice to have something tested, and different stone columns and diameters in every sublayer one can give. Foundation type can be rectangular or circular. Perform settlement calculation using the basic theory of elasticity. Actually, no, you have to use elasticity theory is good for settlement calculations. That is why we use a lot of elasticity theory in settlement evaluations, if you must have seen. And according to there is another method. So, it performs bearing capacity calculations also. So, it generates extensive report of results. This is an advantage, and what I want to say is that one can use some of these methods and do that. So, techniques like this have been quite effective, and there are also a lot of offshoots of this stone columns. So, actually what is that you are doing is that you are trying to create some material inside this soil which is weaker, and if obviously you can do by any means, like if you can say, for example, here it is called aggregate pier. That man says this particular step, like he is trying to create a cavity using auger. See, I do not have a bigger machinery here, I do not want, it is very complicated. What I do here is that I have a simple auger which can be using a simple auger install casing if caving occurs, like if the caving occurs, it is a problem. So, if at all you make an auger, put a casing immediately, some sort of thing, some procedure should work out, and start putting the material and then start compacting like that. Like as I said, stone columns in India, what is called rammed earth stone columns, they are doing like that only, like that. These are all some innovations, like say what they do, place the crushed stone aggregate at the bottom of the cavity, put it here, then ram bottom stone with beveled tamper to produce bulb, then densify crushed stone in layers of 30 centimeters like this, then preload top of the wrap element. So, it is aggregate, it is called aggregate pier. So, the term is, I do not want to call it a stone column, but I call it as aggregate pier. Pier is like a pile, and this is one terminology people use it, and it is good for, you can see that it is good for shallow depths. Say for example, I have a small house which no a big company may not come, but somebody can do like this, is it not? I mean, this is what I find, it is like you have to calculate some properly some of these things and check some quality control. I may not follow any standard method, but then I am very sure that this method works. So, you should be very careful in doing some of these operations, and design also, like proper length and spacing and depth and all that. Like the depth depends on the significant zone of influence, and spacing and all, some of the variables one can calculate, do a parametric study. It is called aggregate pier, and it is quite simple. So, what is the difference, one should know, like in fact it is even done by standard companies. Say for example, what many people, they have different packages for small works, where there is not much, let us do aggregate piers, or if you have a bigger job, bigger loads coming up, you go for stone columns. One can have all these choices, because finally as a ground improvement company, you need to have different approaches to solving the problems. Like if you have simple not the depth is not much, one can use aggregate piers. You can see that the typical length is about 5 to 15 meters in the case of stone columns, whereas about 2 to 8 meters in the case of aggregate piers. Typical spacing 4D here, it could be it is 2D here, and the thickness of the lifts in stone columns 1 meter 1.3 you can just go, whereas here about 20 to 30 centimeters. Allowable foundation pressure, yes, you can get 25 to 150 kPa, here you can go much higher, and typical length to diameter ratio 5 to 30, it can be bigger, it is 2 to 4 here. And construction equipment, yes, I mean little probes and little more detailed, some even as I just mentioned, stone columns also could be conventional, in the sense you may not need high equipment, but nowadays like people, very good companies, they are going for real time monitoring. Like as you construct, I should know exactly how much of stone is inside, and then you come back and make about 2 meters of stone column and immediately run that static cone penetration test, check if that SPT value or CPT value is all right. Like that, people have been doing like that. That is called real time monitoring of structures, and people have been very effective, but then that is very expensive, but of course if the project is very big, one can afford, but in some small projects aggregate piers may be all right. So like here the equipment that we need is about backhoe with 4 meters long tamper and axis, some simple thing. So we obviously the advantages are there, but then disadvantages are also there. It can be economic limitations and performance, the requirement of a drilled cavity, you need a drilled cavity, and the fact that almost all the soils requiring improvement with aggregate piers, they are very soft and compressible, cavity collapse is an inevitable issue. Actually you are trying to use an agar, and before you withdraw, if the cave collapses, it is a problem. So one should have a means of doing it, whether I can leave a casing there or I can withdraw a casing. Some of the issues one should do, like sometimes here the temporary casing is provided, and advanced. Once the backfilling stage onsets, this slowly slows down the application rate and increases the cost per element. Additionally, where the treatment zone depths are required to be greater than 8 meters, aggregate piers shall not be considered as a solution, because they give best performance when used in compressible strata as a floating pile to depths up to 8 meters. So these are all more like a floating piles or a simple reinforcement system, soil reinforcement system, which is quite effective. In fact, people have been using some of these things without much of soil mechanics, because they find that okay, if you intuitively they feel that if you do like this, definitely there will be an improvement in bearing capacity. So that is how people have been able to work out and then do that. So what I do is that I will give some conclusions now and also show you some case studies. For example, I would like to say that we have vibro compaction techniques and vibro replacement techniques. They have been used to a considerable extent in ground improvement projects. They have been very cost effective. In fact, as I said, in some places where they could not do anything, still there is no way. So you need to use ground improvement techniques. Then drainage function of the stone columns has been very useful in the mitigation of damages to liquefaction. In fact, in many places in Japan and all other places where there is a maximum problem of liquefaction, in this technique has been very effective and people have studied very well. Like even people are see the design, what we discussed was about simple static loading, but you should even design the stone columns for earthquake conditions where you have how many number of cycles it can withstand. So for example, how much of pore pressure it can dissipate, because see what we do is that earthquake motion is always converted into equivalent number of cycles of some standard this thing. So how many number of cycles it can withstand, one can design, in fact one should do some more detailed studies on some of these things in using stone columns, and one can really come out with proper measures. Say for example, particularly in earthquake conditions, the drainage or the dissipation of pore pressure is very important, and so you need to design for the magnitude of the earthquake and the number of cycles of that same earthquake, and also its pore pressure dissipation, all that. So, one should be very people have to really do a rigorous job in some of these things. Then what I would like to do is some case studies here, which are actually I must thank the company Keller's company for providing some of these case studies. We'll again this come out, we'll have some specific case studies which have related to tank farm, ports, shipyards, power plants and railways. And of course, the introduction we have seen that they have this type of vibrators which you have seen, like it has a hose, is an eccentric weight, then it has that water jetting and flexible coupling and extension tubes, where if you want to increase the diameter of the or the diameter depth of the depth. So, you have this thing, and this is how it is done, that eccentric weight movement and horizontal movement, that is what we are discussing, how that force is generated and then transferred to that. And as I just mentioned, it is applicable to vibro compaction is very good here, and vibro replacement is very good here. So, this and essentially is a function of the soil type, and we have seen some of these things, how it helps the overall stiffness of the compressible material, and allows also the rapid consolidation by providing radial drainage. So, in fact, there are methods also here. One should actually I will say it is called wet method and also dry method, in which the water presence of you have only the stone being put in here, okay. Then here you have a jetting action and other things. We call it wet top. This is again another way of doing this. You have penetration, flushing, column construction and completion. So, this is a dry bottom feed method of installation, where you try to do in this manner. You have a penetration, delivery and compaction process of stones, completion. So, these are some differences that we have. Anyhow, there are some based on installation techniques, and in the offshore also they do it, like you have a stiff medium clay, you have a barge, in a vehicle you should, I mean in a way this thing you have to take that, and then you have stone columns that are formed here in the soft medium clay, and that is what it is very important that you have to have this sort of structures. So, quality assurance and quality checks are also important, and people do real time computerized monitoring, as I just mentioned. You need to have the CPT profiles and all that very clearly, otherwise with the date and all the information. That is what many of the companies do, like good companies which are like Keller and all that, they do. And this is a typical load displacement curve, like settlement versus load. This is what I was just mentioning, and first cycle, then load and unload, again second cycle. So, you must be able to understand what is a typical load displacement curve using a plate load test. And see, we are used to like I showed you that Kentledge arrangement in the say for example, IS code specifies a Kentledge arrangement which is rather cumbersome, whereas in these people have done a simple case, say 400 tons on 4x4 250 kPa. So, to make it believe that you have a platform of 4x4 and then load 400 tons. So, measure this is how they do it. So, if you want to really see the diameter, you should be able to do that quality control, measure the diameter, and so it has been very well used to many applications like tank foundations, particularly soft soils, ports, slope stability, like as I just mentioned, slope stability is another important issue. Reinforced earth walls, actually in some places where the bearing capacity of the reinforced soil wall is very poor, you need to have foundations like this. Then isolated footings also it can be done, railways people have done, highway embankments people have done. So, we will just see some of the case studies they have provided to us. And the oil tank farm in a Paradip, I will just see that the boundary is IOCL. It has 15 number of tanks with 60,000 kiloliter the capacity. You can see that the height is and all that. The soil conditions are that it is a reclaimed soil followed by 3 meters clay, and it is loose to medium dense fine sands up to a depth of 10 meters, and then you have a dense soil layer at 10 meters below the ground level. So, the problem is that 16 ton per meter square is required and tolerable settlement is 200 mm. So, what they did was vibro stone column of diameter 800 with triangular grid spacing of 2 meters and center to center up to a depth of 10 meters was used. So, they are also using 2 extra columns on that case, and this is the way that they are trying to do. Total length of the stone columns is about 1,60,000 linear meters like length. So, they were able to use 4 rigs, because you need to mobilize you need to speed up the construction processes. So, you need to have more rigs to do that. Installation period 8 months. So, routine group column load tests were performed. You should do a column for the stone columns, group column tests, hydro tests are also done, and settlements are wanted, and which were below 100 mm. That is one thing that was okay. There is another case study that we see, a port structure. It is again, it is very interesting in Vallarpadam in Cochin. You can see that this is the area constructed. In fact, this is what Dr. Venu was mentioning, that it was a very challenging job for them to do this. So, it is again a 600 meters long quay wall and the associated container yard. The deck has a slope of 1:3, this is this thing. Soil conditions, 20 meters of thick soft soil, okay. It is a fill, 2 meter, first 2 to 3 meters is a fill, and it is quite tough, and there is another medium stiff material. So, the issue is that slope stability is an issue, settlement control is an issue, and the solution was that they have done a design, a rigorous design, and then came out with a configuration of 1.1 meter diameter stone columns with a spacing of 2.1 center to center. Then the depth is about 22.5 meters, you can see the depth. Then the length of the see total stone columns, like you say about 22.5 meters into number of columns, it gives the linear meter length of the stone columns. As I said, again the 4 rigs were used here, installation period 8 months. So, the beauty is that within 8 to 9 months or 1 year they are able to finish the project. Normally you know that you can't recover the area, but then you are using a ground improvement technique within a period of less than a year, they are able to see that this ground is ready, you can do something, construct whatever you want. That is something very interesting. There is another case study that we have, and it is again in Pipavav shipyard, Gujarat. Actually, I think I should as I just mentioned, they have been very kind to spare some of the information here, and again you have a quay wall here, and soil conditions or something, SPT value is very 9, and then it has a marine clay of 4 to 6, you can see that it is quite tough. And then you have fortunately another weathered rock at the bottom. Of course, problems are that definitely when you have such a soft soil of SPT, such a low number, you have to have settlement problems. So, limit the settlements, increase the bearing capacity for hard standing payments. Bearing capacity requirements, say for example, they have to construct payments on such materials. So, you need to have a good bearing capacity. So, they want to have even good bearing capacity for payments. So, solution again, vibro stone column of 900 mm diameter with triangular grid spacing of 2.5 meters center to center. Okay. So, the vibro stone columns extended up to 15 meters depth. This is another important point. It's then So, this is the way it is done. You can see that you have stone columns here, hard strata, dry dock, all these are all stone columns. It's see, they need to have the sort of arrangement which is very complicated, in the sense it's not easy, like dry dock is here, then you have assembly of the ship here in an area that has so much poor soil. It is not easy, and again here the total length of the stone columns is about 1000, length used is 1.44 lakhs, I mean it is linear meters, 1 point or 1, I mean it is 1,44,000 meters. At peak again they were using 4 rigs, I think they had this constant installation period 10 months, it is quite good. Then we have some more case studies on power plants, like in Chennai, it is a background, say NTPC is the owner, cooling towers, they have soil conditions, subsoil has 7 to 9 meters of soft soil, SPT value 0 to 6, and again it has a dense sand, SPT 12, it is actually less than 15 is very poor, like it is very difficult. Say for example, in a clay SPT value is also somewhat meaningless, because there is a water table, we do not know what exactly it means. Then you have finally a clay sand with SPT of 25, and that is okay. So, the issue here is, as usual, increase the bearing capacity and limit the settlements, and solution is that of course they came out with their own calculations and methods, and then actually these people take some projects, then they have to design, they have to show that it works, and in this case they were able to show that 900 meter diameter triangular grid spacing varying from 2 meters to 2.4 center to center was used, and the columns extended up to 11 meters, and this is the case. You can see that soft soil is here, clay sand is here, then medium sand. So, you have a stone column in this form, that is very useful. So, these are all number of columns, this so many, I mean 3 lakh, or they call it 300,000 linear meters of stone columns were used, and installation period it took more time, 20 months here. Then another one which they have, it is in Delhi, and of course you have some material like this, soil conditions, again SPT value is very low, 5 to 10, dense sandy material SPT, again it has a the seismic zone, it comes in a seismic zone, and the peak ground acceleration design should be 0.24, and so the issue is again the bearing capacity improvement, and here as I just said, even the earthquake potential, liquefaction potential is to be, we should check for the liquefaction potential, and also see that the liquefaction possibilities are minimal or do not exist at all, we should reduce that. So, they are able to see that circular tank here, and then the stone columns of 500 meters, 500 mm diameter with a triangular grid of 2 by 2 meters center to center was used. So, this is what it is, and they extended from up to 8 to 12 meters below the ground level, and so these are all some of the details again. They have used a displacement method, installation period is 8 weeks, and this is another case study on railways, in railways where they are trying to look at again the problem here again is again a soft silty sand layer of 7 meters thick, and the soil is susceptible to liquefaction, and because the peak ground acceleration is 0.24 g, which you should do in the design. And geotechnical problem is that essentially it is liquefaction resistance one should provide, and the solution is that, as again they came out with 750 mm diameter at 2.8 meter center, and then they extend up to 12 meters, and again the length of the stone columns used was 11,000 linear meters, and one rig was used. Of course, it must be a small project. Installation period is about 2 months. So, I am sure that with many of these ground improvement techniques in practice, there is a great deal of one can understand this the ground improvement the stone columns as a viable method for improvement of ground. And I should say that somehow there are many issues there. Actually, I was just mentioning that apart from I said I was also talking about stress strain properties of the stone as well as clay soil, and also I was mentioning about the confinement of the stone columns. So, I would like to talk about this much more detail in this these two things, because I see that the confinement concept is very interesting, in the sense that you have a stone column, you put some sort of confinement, and then people have done lot of studies. In fact, people have done lot of research, like particularly in the form of PhDs, at least a couple of 5-6 PhDs are there in this area, which talk about use of confinement in the stone columns, because the advantage of the confinement is that actually you can reduce a stone quantity itself. There are two issues here. One is that you are trying to avoid that failure mechanism. Actually, we discussed about different types of failure mechanism, like something occurring at the top, like and then something occurring at the bottom and all that. So, particularly bulging occurs at the top, and then or if there is a it is a shallow stone column, the possibility is that the failure surface develops there itself. So, if you want to really avoid that, one can really provide confined stone columns, which will number one, because of the hoop stress that is generated. The thing is, what you are doing is that now the another design variable is coming, that see, you are trying to provide some sort of confinement pressure using a circular member. So, that introduces some sort of hoop stress, and say you can have different types of material. You have a loose material like a geotextile, you can have it gives a confinement. You can have a stiff material like a geogrid, can have a confinement. You may have some other stiffer material. So, what I meant was that stiffness of this encasement, what you call, is very useful, and one can really do a lot of analysis on this. The thing is, people have done lot of work on, particularly doctoral programs. I have seen at least 3 or 4 theses, and some more field studies in Germany, where there people are trying to work out on this. And another significant role that I find is that in terms of more the practical applications, like this will particularly the encased stone columns will lead to lot of savings in aggregates also. Say for example, in a particular project, if you are using some amount of aggregates, and if it can reduce by some 30% that aggregate or 40%, definitely it is going to be very effective. And this confinement is nothing but geogrids one can have, and they are polyplastic material, one can use them. So, that is one important point. And from research point of view, I find that it is a lot of scope for numerical analysis, design, guidelines and all that, because you have to generate design for hoop stress. So, the design procedure is somewhat different now, because earlier we are trying to design for from limit equilibrium methods. We assume that there is a cavity expansion, and then there is a resistance because of the lateral pressure. So, you are trying to do this, that is one but here you have another variable that is coming in, which is in the form of a hoop stress or the stiffness of the geo material that you are using. It can be a geogrid or any other material, and lot of papers have come on this in the recent times, how it can be done, and a lot of laboratory work is done, lot of numerical work, in the sense using Plaxis, using FLAC, lot of work has been done, and that has been a very useful contribution. And apart from it, I see, you people have exploited these techniques in Japan, because particularly the use of what you call this both confinement effect and even this drainage, the drainage function of the stone columns. It is a very valuable system where you are trying to design for how much of pore pressure is mobilized because of that earthquake and how much it can be reduced and how many number of cycles it can withstand. So, there is some sort of refinement in risk analysis also is being done. So, what I find is that these the stone columns in whatever form, like they are essentially column inclusions, it is more like a reinforcing the ground. It can be from stone columns just alone, it can be with just sand compaction piles. People are using different terms, actually if you just look at literature, people are using different terms, but the only actual thing that comes out is that it is working as a reinforcement in the vertical direction, because there is a load applied and then you have some columns that are taking the load, and the load coming on the other soil which is a native soil is less. So, the column inclusions have been very effective. You can call it a stone column, you can call it a sand pile, you can call it a compaction pile, you can call they are all different. So, the thing is, as I just mentioned, there are two types, one is vibro compaction and then the other one is vibro replacement. Methods in a way are similar, but then in some place you are using stone columns. So, because its stone is available, you can use flash, you can use so for example, there is a thermal plant and then you can use a flash nearby, and then there is a soft soil, you can you can use many things. And so, it is not that like the companies are some companies have standard protocols, because they have established there some efficient process of using their own techniques. But then at the same time, it is possible for us to try to optimize on designs by using varieties of ways, like see even this aggregate pairs, rammed aggregate pairs, they call it RAP, we must have seen the word RAP, rammed aggregate pair. Even that is good enough. In fact, for small buildings of 40 by 50 site if you have, and if you want to increase the bearing capacity, what you just need is that you need an auger, and then you just put some sort of start ramming it, and then constructing it, and then coming to some, say for example 5 meters or 6 meters, then put some sand layer here, that is it. You do not need a big contractor to operate some of these things. These are all simple, then you should do some make sure that the design is correct, because it involves some design and also some spacing, length and all that one should work out. And if you are able to work out some of these design details properly, I think you have a lot of solutions for some of these materials, and this has a significant role. So, with this I feel that we have some more case studies on stone columns, particularly on the varieties of stone columns, like as I just mentioned, even the rammed earth technique, you have some case studies one can have, and then even case studies on the use of what you call the confined geocell, confined stone columns, whatever. So, you have a lot of techniques. So, but I think one should go through the literature, because ground movement technique is the area that that has still long time to go, because when sites are limited and then the infrastructure is growing, even you may have to end up doing ground movement projects on moon. There is no other substitute. Thank you.